Hi, welcome everyone. We're really thrilled to have you here at our webinar to do the launch of J0927, codename J0927, the world's fastest NewSQL database. Today, we're going to go over an introduction to J0927, what the key features of J0927 are, use cases for J0927 so you can put it into action, and a technical overview so you have a greater understanding of our NewSQL database. So just to give you a little bit more background on J0927, which is the world's fastest NewSQL database and the only featured database. There was a star that was just discovered named J0927. It's the fastest star in the galaxy. And so we named as a code name our NewSQL database, which is the fastest in the galaxy, and it never stops running with 6 nines availability, J0927. Although we're emerging from stealth mode right now, we have tens of thousands of enterprise installations that are already running around the world. Our technology is in production via Oracle, deployments that are powered by the technology that we invented. J0927 is the only database available in the market today that meets all of the requirements listed below. I'm going to go through them pretty quick here, and Mikhail will go through them in more detail during this presentation. J0927 is the only database that has high fidelity, no corruption, ACID, and two-phase commit. It has low latency reads and writes. Data and compute is close to the distributed end users. There's fresh data, whether it's high volumes or high velocity. It's always running, parallelized SQL, and there's a low cost and easy to use tiered storage model. As you can see, some of the key technical features below, we're able to perform low millisecond range while scaling horizontally or linearly for reads and writes. We're the only NewSQL database with two-phase commit and serializable isolation out of the box. Additionally, we have data that resides closer to users for reads and writes. Another feature that's out of the box is time travel. We're also designed from scratch to support a seamless CI/CD process. And lastly, we're one step away from being the only homeopathic database, which is self-healing and self-tuning. And we're able to make DDL and rebalancing changes on the fly. So welcome to the webinar. I'm going to tell you a little bit about us just so that you get to know us better. If there's any questions during the webinar, please ask them, and we'll answer all the questions at the end of the webinar. So to introduce you to Dr. Mikhail Ronstrom, he's a world-renowned database expert. When he was working at Ericsson, he founded the NDB cluster, which is an open source project that is now acquired by Oracle, and it powers 40,000 plus mission critical installations. Mikhail joined HopsWorks as the head of data and forked the same project in order to modernize it. And I'm your host, Nathan Greenhut. I've got over 20 years of experience at Fortune 500 companies and government institutions. I've directed large-scale data modernization and applied intelligence projects, and also AI and ML projects. And I am the head of accounts for the Americas. Should you need any information from us after the webinar too, please reach out to us via our Slack channel, which I'll put into the Q&A. And you can reach out to us directly. I'm going to hand it over to Mikhail, who's going to walk you through more details on J0927.
Okay, thank you, Nathan. So the first step is just to sort of try to visualize what kind of use cases we have for J0927. So if we start on the top left, online feature store. So J0927 is developed in a company called Hopsworks. And what we do there is effectively developing an online feature store. So that means that you sort of can optimize your machine learning by having hundreds of thousands of online features continuously changing and serve thousands of machine learning models. So the actual data for these features comes from external systems. So we have an event-based real-time feeds that feeds into J0927. And all of this can actually be done also with multiple regions, so that if you have one region going down, you can fail over to another region. We have availability both inside the region and between regions. So that's how we can achieve 6 nines of availability for the online feature store. And we have this more or less in production already. So it's not just playing around with it, it's there working. Distributed payments and financial ledger and online banking, that's another very important use case. About the installations that was mentioned before, there are lots of installations that do this, that do millions of transactions every second. And there are tens of millions of users that are making payments based on these systems. Online gaming, there are lots of games that use needs this type of system and use it as well. So there could be that you have the real-time state of the games. It could be that you have the profiles of the users in the database for logging in and so forth. So that lots of cases where you can use the fastest key value database to use it for online gaming. We have subscriber and visitor insights personalized recommendations. So a few years ago, we did a benchmark together with Spotify, and they had a case where they did personalized recommendations in their search system. And so by doing that, you had like hundreds of queries to the database in order to give you a personal recommendation. And so they did some benchmarking on that and showed that this database was the fastest one available. Global design is another example. So we have thousands of designers working on a chip design, and those chip designers could be working in different parts of the world. So you could have more or less an active scenario where you have several regions updating the database at sort of as time goes by. So this is an important one that has to be available all the time. And finally, we go to identity and access management, networking, and cybersecurity. I mean, this was where this NDB cluster that was mentioned was starting first customer was in this area 20 years ago. So that was high availability is extremely important, obviously, because if your networking system goes down, then, well, you don't really have any way to go without the network. Okay, so what you find here is that you need data and compute close to the distributed end users, and we need low latency. We need high number of reads and writes so that it scales. The data is always updated, so it needs to be fresh. There's a high volume of data and they're constantly updated. It's always running. It needs to be sort of high fidelity. So, I mean, so you have to have consistent data coming out of the system. So that's sort of the background. So if you look at J0927, the first question is, do we have full availability during recovery and during CI/CD? And the answer is yes, we do have that. So you can read your database while you're recovering. You can write your database while you're recovering. You can read and write your database even when you're doing complex schema changes, while you're doing complex changes of the cluster. You can add nodes, you can change nodes, you can change the clients in the system, and so forth. The second thing is tiered storage. So most of the databases in this area is in-memory databases because of the extreme requirements on latency. However, lately we've seen the development of NVMe drives that are almost as fast as memory. So what we have done there is that we have made it possible to choose whether you want to have the storage in memory or whether you want to store things on disk. So on disk obviously means that you have a much lower price, but there is a slight sort of higher latency, slightly lower throughput, but you get 10 times more data for a 30% higher price. So that's probably something that's quite important as well. So low cost is also possible with J0927. Read-write scalability, yep, it's a distributed database and it can scale to many nodes, many CPUs. Thousands and thousands of CPUs can be in the cluster. So we'll show more about that. Security, it has a lot of security features. It has ease of use. There is actually a multitude of APIs. You can use it with SQL, you can use it with LDAP, you can use it with REST APIs, you can use it with the sort of some specialized APIs that's only available for J0927. It's got the highest performance. Actually, already 10 years ago, we showed how you can do 200 million reads per second. And if we were to do the same thing today, it would be billions of reads per second that we would be able to do. And a funny thing is the distributed sharded serverless at the AWS reInvent yesterday, they had a question where they said, what is a sort of distributed sharded serverless database? And I was immediately thinking, well, it's J0927. So we actually have a serverless HopsWorks installation already now, and we will have one for J0927 as well. And we have the lowest latency. So even down to microseconds in some cases. So this is how the sort of J0927 architecture looks like. There are data nodes. So you could think of the data nodes as that's where the data resides. Sorry, there's some building of a tunnel beneath me. So they're doing some stuff. So that's what you heard here. Sorry about that little interference. So as I mentioned, the data nodes is where the data actually resides. So there could be a multitude of data nodes. And then you have a number of ways to access the data. So here it's showing the MySQL servers, but you could also have REST APIs. You could have specialized API nodes that have specialized software to introduce things. So for example, you could have a Java application running very close to the data nodes. So moving forward, so performance, we already mentioned that we have low latency. We can attach REST APIs. We can have, in the HopsWorks idea, we have Kafka that is used to get data from other databases and into this feature store database. We also have Flink connectors for streaming data. And we do have both sharding inside the region and between the regions. You can have sort of sharding on two levels here so that you can get your data closer to the end user for both reads and writes. So if we start with read scalability, it scales horizontally for reads. So basically what happens is that we distribute the data on a row level. So we have a partition key, and this partition key is something you define when you create the table, and then we automatically shard using this partition key. And if you have a setup where you have, for example, data distributed in 3 availability zones, then we will actually make sure that you access the data from, if you access from one availability zone, we'll make sure that your reads goes to the availability zone where you are, so that you get the lowest latency possible. We have automatic parallelization and distribution of both simple and complex queries. And so the complex queries are pushed down to the data nodes for using a scheme we call linked merge join. So we have a fair amount of parallelization that can happen automatically. We have write scalability. So it scales horizontally for writes in more or less the same way as it does for reads. That when you write, you update all the replicas, and there are normally 3 replicas in a cluster, but you can also run with 2 replicas and be more or less as safe as with 2 replicas, as with 3 replicas, I mean. We have multi-master within region. So effectively, in the region, you can write to any of the data nodes. You can have any cross-partition transactions, and it will be just fine. When you have replication, when you have an active setup between regions, then you also have to have conflict detection, because obviously the speed of light makes it impossible to lock things for hundreds of milliseconds. So in that case, you can have a conflict detection algorithms, and there are a choice of 4 or 5 different conflict detection algorithms to choose from. And we also have a number of tools to import data, like NDB import, NDB restore for restoring backups. And we, in HopsWorks, we have something we call online FS, which is used to get data from Kafka into J0927. We have ACID compliance, so we have a 2-phase commit. And sometimes you think about 2-phase commit as, well, it's blocking. Well, it's actually not blocking in our case, because if a transaction coordinator fails, there will be another coordinator that will take over all the work of the failed coordinator. So there will never be a blocked case in our case. And we have isolation levels. So if you want to have very advanced isolation, you can always use application level locking. And we do have locking on rows. So any kind of row level locking is serializable in our case. We do persist transaction to disk, so that you can always, even if data is in memory, you can always recover data later on. And we also actually have, we will talk more about that in a future webinar, but we also do have this J0927 is actually also a distributed file system built on top of it. And built on this file system, you can use Hoodie, and that gives you time traveling and all sorts of other interesting facilities. So you can actually see this as a real-time database for online features, but it also is a very important part of the solution also for the offline activities. So basically the places where you do the really complex queries and train your data and do all of those things. Schema changes are atomic. So if the schema change fails in the middle, it will be rolled back. Okay. So moving on, availability. So availability, if your data, if your cluster is completely within one region, you can reach around about 5 nines of downtime of availability, I mean, which means that you have less than 5 minutes of downtime per year. If you actually also have clusters that span regions, so that you have replication from one region to another, you can get 6 nines. So an interesting case here for NDB was that We had a customer that had thousands of installation, and they had 0 downtime for about 10 years. So that's pretty good. Obviously, when you actually get a downtime, it's usually an outage, and that outage, as usual, takes a bit of time. I mean, we're still humans, so we can still make mistakes. And there is a seamless disaster recovery at the database layer, so that all of those availability things happens automatically. We have security. I mean, in order to be serverless, you have to be certified to actually maintain other people's data. So that certification is called ISO 27001. We're also SOC 2 compliant. We do have, or will soon have, both at-rest and in-flight encryption of data. Already mentioned tiered storage. We have a Kubernetes feature in development, so very soon we will be able to use this completely within Kubernetes. We already have elastic autoscaling, so basically if you create your own cluster in, for example, in Google Cloud or AWS or Azure, we have the ability to scale that with new MySQL servers, changed MySQL servers. The data nodes can also be scaled up and down. So that already exists as a feature, and you can run it either in your own cloud or have us run it for you in our cloud. We do have a REST API. We decided that there are a number of things that make it a lot easier to program if you can have a REST API. So we designed that, and particularly we have focused on the key lookups for that, and also batch key lookups, so you can effectively send one REST API call that reads 200 rows as one query. So that's something that's pretty popular. For example, this personalized search that I mentioned before uses that feature. And then we do have integration with Grafana, Prometheus. We have integrations with Flink, Spark, Kafka. As mentioned, we have SQL, which means that we have JDBC, ODBC. We do have auto failure detection and handling. Failover, well, easy might not be the right word for global failover. I mean, you still have to sort of manage. Global failover will be manual, so you don't want to sort of fail over automatically, because it's usually somebody that has to sit there, and if you want to be sort of perfectly sure about failing over from one region to another. There is a lot of automatic load balancing, and we can even do shard rebalancing on the fly without taking down the system, and completely non-interrupted. CI/CD, so we can survive multiple node crashes in one cluster. We can handle add column while writes happen. We can add and drop indexes and foreign keys while writes happens. We can add new shards and reorganize data to the new shards while writing. We can perform software upgrade while writing. We can even skip versions and do sort of multiple version steps in one go. So quite advanced on that. So if we focus on performance, performance is a very important part, and we have very high throughput. I mean, we are not calling ourselves the fastest key value database without having benchmarks to show it. And we've been showing that for a long time. So you can have peak on low latency. You can do a primary key lookup in parts of a millisecond. So you can get down even below hundreds of microseconds. You can get down to tens of microseconds. And if you're in the same machine using shared memory, you can probably go down below tens of microseconds even. We also have batch primary key lookup. I mentioned that we use that from the REST API. So you can send hundreds of row primary key lookups and get all of them responded to within a few milliseconds. And that's a very important part when you do online machine learning and online feature stores. Another important aspect is you have left outer join. When you have a star schema of 10 tables, you want to do a left outer join, and that basically is also something that can be done in our benchmarks with Sysbench and modified Sysbench. We managed to do a left outer join in about 1.5 milliseconds. So that's pretty great performance in a distributed cloud setup. And as mentioned, we have REST API, Flink, Kafka. We have the ability to read the nearest copy inside a region. And when you do region-to-region replication, you can obviously choose which region you want to go to. You can go to the nearest one so that you minimize the latency. We already mentioned a bit more detail on read scalability. So we mentioned that we shard on partition key. So you decide on which partition key. And that decision on partition key is obviously pretty important, because that means that all the queries where you know the partition key will be going directly to the data. But if it happens that for a query you don't know the partition key, we'll still be able to do the query. So we'll just have to send the query to all the partitions and find out where the data actually resides. And in a multi-availability zone region, you have the automatic routing of reads to nearest copy. So that's pretty important. I mean, for example, in AWS, you have a 2 millisecond delay latency just going to another availability zone. Whereas inside availability zones, you might be getting to another node within 50 microseconds. So it's a very big difference between going to copy inside the same availability zone compared to going to a different availability zone. So it could be a difference of, as I mentioned, about a factor of 40, 50. So, and we have that automated so that you do it always go to the nearest copy. We also, inside the data node, we have a quite advanced load balancing scheme. So if you have a machine with 32 CPUs, we automatically route the read request to the least loaded thread. So in that way, we manage to sort of have a very quick execution of the queries, but at the same time, we also manage to use all the CPUs for the queries. And as mentioned, we also can have pretty complex queries where we push down the join operations and automatically parallelize them as part of the query execution. Yeah, so same thing more or less for writes, that we also scales horizontally for writes. We've done benchmarks where we've been doing many, many millions of writes per second. So I would guess that we would be able to do at least a few 100 millions per second in a big cluster today. And what we do when we start a transaction, we place the transaction coordinator close to the data automatically. And we do have full support of distributed transaction inside J0927. So there's sort of nothing you can't sort of, there's no transactions. I mean, we don't want you to have transactions that are like updating billions of rows in one transaction. But if you do moderate sized transactions with hundreds of thousands of rows, it's up to that. It's just fine to do distributed transaction. And you can have bigger than that if you like as well, but that's probably not recommended, because then obviously you lock the rows and you're not really a real-time system anymore. And we have a number of parallel load facilities. Okay, write scalability between these different clusters. So we have transaction consistent replication from one cluster to another. And you can either set that up as an active passive replication. And in that case, we have dual channel replication channels so that you can fail over from one channel to another. Even if one channel goes down, you continue to replicate even in that case. And if you have a problem that your primary cluster goes down, then the replica cluster can take over. So there is failure support for that. You can also have active-active replication. So you can actually have one cluster in the west coast of US and one cluster in the east coast of US, and they replicate both to each other, and you can update in both clusters. In that case, we have conflict detection so that you can find out if there is a conflict that two transactions try to update the same things at the same time, then you get conflict detection to sort of figure out how to handle that. And there are 4 or 5 different variants of how to do that conflict detection. Accuracy, we do have ACID support. We are atomic through the two-phase commit protocol. And the two-phase commit protocol, as mentioned, is non-blocking. We do have serializable isolation, but through row-level locks. So that means that if you need to have higher levels of isolation, where you even want to sort of make sure that you have like locking ranges, then you have to do that on the application level. We persist transactions to disk media with transaction consistency, and we do have atomic schema changes. And as mentioned, HopsWorks is ISO 27001 certified. That means that we have the ability to take care of your data if you like to. We can run the database in our cloud and manage it, and we are certified that we are sort of good to do that. So we run through all that certification. HopsWorks is also SOC 2 Type 2 certified. J0927 have at-rest encryption, so that you can actually specify that, so that the sort of, even if you get root access to the machine, you still won't be able to read the database data. And very soon there will also be in-flight encryption, so that any data that travels through the system will be encrypted. Availability. So we mentioned that with region-to-region replication, you can get 6 nines of availability. That means less than 30 seconds of downtime per year. If you're only doing clustering within the region, then there is a few things that might need some downtime, but 5 nines is definitely possible, which is less than 5 minutes of downtime per year, even with a single region. Of course, we cannot be more available than if you're running in a cloud, then if that cloud has less availability, we can obviously not be better than the cloud. But if you are on-prem and you maintain your own, then we can definitely get to that. Okay. Columns can be stored in memory or on disk. So for optimal performance and latency, index columns are always in memory, so that we can make fairly complex queries, even sort of with very low latency. So obviously in-memory provides the optimal throughput and latency, but on disk provides a much lower cost. So you get 10 times more data roughly at 30% higher cost. And we have done some benchmarks that you can find at rondeby.com, where we've showed that on disk, in those benchmarks, we've seen that on disk has maybe 2-3 times higher latency and lower throughput, but it's still very good throughput and latency compared to any other database, key value database you'll compare with. We outperform everyone that I know of, at least. And then since we are a part of have a MySQL API, that means that all the MySQL APIs we have available. We have a C++ NDB API that's for if you really want to go to the lowest level, you can use that. On top of that, we have a ClusterJ a Java API that you can use. So quite a few of the HopsWorks applications use the cluster J code. So for example, this distributed file system that's built on top of J0927 is built on top of cluster J. There's also a Node.js NDB API as well. There's even a common Lisp NDB API that was contributed by an external, by the community. We do have an open LDAP extension, so you can actually run LDAP on top of J0927. Another community extension is that you can actually run RDF on top of J0927. We do have a REST API, and we are definitely going to continuously develop this REST API so that it gets more and more advanced. There is another community product called Flink NDB, which is effectively using J0927 and to run a Flink cluster. In HopsWorks, we have a Kafka service, we have Spark integrated in HopsFS, and we have, as mentioned, this HopsFS distributed file system built on top of J0927. So automatic load balancing. New transactions, they're started on the data node owning the first row use. So that's an automatic sort of, so if you have a very short transaction, it will basically go to the place where you have your data. If you have a more complex transaction, then it will be by going to the first row use, you will actually get automatic sort of round robin, because data is, the place where data resides is decided by a very advanced hash algorithm. So that means that it becomes more or less random. I mean, you can spend a few years computing to make two rows happen in the same place, but I guess that's a waste of time. So all write operations are sent to all alive nodes. So it's a write all available scheme in the node group. So we actually have node groups so that it's more or less the same thing as a shard. The nice thing with that is that we can handle very many failures at the same time. So as long as we have a majority of the nodes still alive, then we know that we can continue as long as we have at least one node in each shard. And even in the case where 50% of the nodes have gone away, we have the ability to have an arbitrator that decides which one to continue. So in the case of network partitioning, we will still be able to continue operating in one of the partitions. Locked read partition operations are sent to the primary replica node in principle to avoid deadlocks. Read committed operations are sent to the closest replica. So we have a concept we call location domain ID on each node, which basically tells us which availability zone we're operating in. So this is something we set up in the configuration. Distribution of read operations is load balanced internally in a data node, and it's rebalanced many thousands of times per second. Actually, when I did this work, I felt like I was almost going into philosophy about how time happens. It's kind of interesting to where you have a single computer and still you have the speed of light affecting things in a dramatic way. So, but we do have a rebalancing happening so the rebalancing happens within 400 microseconds. So if you have a change of load, 400 microseconds later, we have changed the sort of distribution of reads according to that scheme. And we also make sure that whatever reads we do, we always target a CPU which shares L3 CPU cache with where the data resides. Ease of use, we do have Grafana Prometheus dashboards, 12 dashboards with numerous graphs. So we probably have 60 to 70 different graphs showing how the cluster behaves. We have automated failure detection. We handle failures automatically, completely automated. And even the restarts happen automatically if you decide that they should do so. And we have worked quite hard on managing J0927. So we have elastic auto-scaling. So that means that you can automatically scale the number of MySQL servers and the number of data nodes, both upwards and downwards. You can change the VM types of those. So for example, if you have a case where in the night there's very little activity, well, then you shut down the number of MySQL servers and keep as many, or you could put them on smaller VMs. And then when you go to the busy hour, you scale up so that you use the MySQL servers have much more capacity to handle things. Or if you use REST API, the same reasoning. And then we have the global replication between clusters, as mentioned, and you can automate. We have automated the failover of replication channels, so it will detect if there is a problem with the replication channel and automatically fail over to the other channel. There is manual failover to the other region because that's a little bit more complex, and you don't really want sort of automate. I mean, it's quite difficult to discover in a complete in the world where the problem is. So that's where we rely on humans to actually decide which region to be in. But active region can be done with conflict detection, and there's numerous such available. Multiple failures. So this just shows a case where you have two node groups, 3 nodes in each node group, and we can survive any single failure. In this case, we can survive any double failure. So you choose 2 nodes in this case, and we will survive all of them. Triple failure, we will survive some of them. So for example, if 1, 2, and 4 fails, and the arbitrator is still alive, we will survive. If 1, 2, and 3 fails, no, we will not survive that because the whole node group is gone. So the node group concept means that we can actually handle multiple failures very, very nicely. So that's very good. We can also add node groups on the fly. So for example, let's say that we have one node group with 3 nodes to start with, and now we add 4, 5, and 6. So we first reconfigure to introduce the new data nodes. Then we add the node group into the as a command so that everyone knows about the node group. And finally, we redistribute the rows table by table. So every table will be sort of repartitioned so that it has partitioned the data into the 6 nodes instead of to the 3 nodes. And through the entire process, you can write in the tables. There's no downtime for neither reads nor writes. And you basically get twice the amount of CPUs and twice the number of memory in doing this change. We can have the add column while writes happens. We can have add drop and foreign keys while writes happen. And we can have software upgrade and downgrade while writing. Even software downgrade we can handle. So that's pretty important. So finally, how do you see this as a sort of in the global scale? We have J0927 as the sort of the baseline, the platform, the technology system that we build things on. And then you have all sorts of machine learning driven applications like the feature store itself, the personal recommendations, distributed payments, gaming, global design, anti-fraud. We've shown series, very good examples of how you do money laundering and anti-fraud using HopsWorks, credit risk checking, identity and access management. So that basically completes. Now on to questions.
First of all, thank you for that thrilling webinar presentation. I found it super insightful. We do have a few questions. So the first one is, will we get the recordings and will we get the slide where? And I answered that. There's a YouTube channel. If you go on YouTube and search for HopsWorks, you will get to the video. When it's posted, it should be posted in the next couple of days. If you'd like to receive any of the slides, please reach out to me directly at nathan.greenhut@hopsworks.ai. I'm going to go to the other questions. So the first question was asked by Valentina, and I'll give just a short response, Mikhail. My thoughts right before you go. But the question is, could you tell me more about the semantic layer feature? I don't think I've seen this in any other database. And the first thought that came to my mind was like a semantic layer kind of stores the mappings, and the mappings can be among metadata or data or end data. And J0927 is often used to store large volumes of metadata as well. Mikhail, what are your thoughts in regards
Yeah,
to the
I could mention that in HopsWorks, we have more or less three things that the J0927 is used for. So one thing is obviously this distributed file system. The other one is the online feature store, where we have more or less each feature group being a table. But we do also have the metadata of sort of what are those tables actually meaning. I mean, so all the metadata of how to actually understand the data is also stored in J0927.
Great.
And we actually in the REST API, we have the ability in the REST API, you can actually ask either you could ask the database for information, or you can ask the feature store for information. And if you ask the feature store for information, it actually looks at the metadata before it actually goes to the database.
Wonderful. I'm going to ask you some other questions that came in through Slack as well. So when you release minor versions, do they break applications?
Minor version update should be more or less free from that. That's the idea. They should be sort of, I mean, obviously, when you upgrade, you have to upgrade in a sort of safe way. So you have to upgrade using a rolling restart. But the intention is that this should never break any applications for sure. I mean, in the last 3 years, we haven't done any change of the NDB API whatsoever, other than 1 or 2 bug fixes. So the application should just continue to operate even with minor versions, and in almost all the cases, even with major version updates.
Great. And I have one final question from Slack as well. If you have ACID transactions and have to persist all writes before they can be read, then how can you be the fastest database for reads at the same time? If you'd like me to repeat it, Mikhail.
No, I think I understood the question. So the way we handle it is that we have the data in memory, and some parts could be on disk, as mentioned. So when you do the actual commit, we have something which we call network durable. So that means that when you commit the data, it's all committed, it's network safe, meaning that it is the commit is in more than one computer. So it's basically in all the computers where you have replicas. At that point in time, when you do the commit, you haven't actually put the data on disk yet. So the actual doing that is a separate checkpoint where you sort of a few milliseconds later, so when you have if you have a complete cluster crash, you could lose, say, 1 second of data or something like that. But
Understood.
But a complete cluster crash is very unusual. And also we have this region to region replication that could sort of make it even less likely.
Thank you, Mikhail. That's the end of our questions. I wanted to just wrap things up really quickly. You can see on the slide, please join our Slack community at public-hopworks.slack.com. Explore our latest tutorials, log into our website to start using HopsWorks, which is which is based on J0927 as well, and ask us any questions. If you need any contact with us or you have any additional questions, feel free to email me at nathan.greenhut@hopsworks.ai. Mikhail, thank you so much for talking with us today about J0927 and the fastest NewSQL database in the entire galaxy. It was a superb discussion, and I wanted to thank our attendees too. Again, if you have any, questions or you'd like some one-to-one information too, more than happy to provide that to you.